Look at a question that covers the Equilibria and rates topic. So we're given some information about the synthesis of methanol. You see it's an equilibrium and we're given the enthalpy change for the reaction. So the first part of the question is telling us that high pressure and low temperature gives the maximum equilibrium yield of methanol, and we have to explain why. We then have to make some kind of comment on why the actual conditions used by the chemical industry might be different. So why do they not use a high pressure and why do they not use a low temperature? Part C, we've got a bit of a choice in this one. So we're given some information about catalysts, and then we're told that chlorine radicals catalyze some reactions, and then you choose a reaction that you've studied that is catalyzed by chlorine radicals. And when I go through the answer, there are two that I'm going to talk about. We have to write down an equation for the overall reaction, and we must show how chlorine radicals are not consumed by the overall reaction. We've got to draw a diagram now using the axes below. Sketch an enthalpy profile diagram for an exothermic reaction to show how a catalyst provides the alternative route with lower activation energy, and we have to label these three things on our diagram. So there's the axes there. Let's make this a little bit smaller so you can see everything. So there it is there. So the final part of the question continues the theme of catalysts, and it's talking about sustainability. So we have to suggest two ways in which the use of catalysts help chemical companies to make their processes more sustainable. So if you have a go, and then I'll go through the answer. So the first part of the question, you can see I've added some extra little bits of information here. As I'm processing this, or as I'm reading through the question, I would advise that you do this. So we've got 3 moles of reactants, 1 mole of product, and that negative 91 means it's exothermic, or the forward reaction is exothermic. So high pressures favour the side with the fewest moles. So in this equilibrium, we've got fewer moles on the right, so high pressure will shift this equilibrium to the right hand side and give us the maximum equilibrium yield. Low temperatures always favour the exothermic direction, and again it's the forward reaction that's exothermic. We know that from that minus sign, so a low temperature will push this equilibrium over to the right hand side. So in practice, the industry wouldn't use those conditions, and that's because high pressures are dangerous and low temperatures, the rate of reaction is too slow. So here's the question, or here's the part where you had a choice. So on the left hand side, I've gone for the catalytic breakdown of ozone by chlorine radicals. Remember, this has to be about chlorine radicals. We had to write down the overall equation for the reaction. So there it is there. So O3 reacts with an oxygen atom to create 2 moles of O2. Now, to show the chlorine radical acting as a catalyst, good idea to put the 2 propagation steps in there. So we've got the chlorine radical reacting with ozone to produce the ClO radical and an O2 molecule, and then that ClO radical feeds into the second propagation step, reacts with an uncombined oxygen atom to reform the Cl radical, and another mole of O2 is produced. When you add those 2 equations together, you create the overall equation, and the ClO radicals cancel, as do the Cl radicals. And then the other reaction you could have gone for, the chlorination of methane. So there's the overall equation. Again, two propagation steps. Chlorine radical combining with CH4 molecule. It strips off a hydrogen, produces a methyl radical and an HCl molecule. The methyl radical feeds into propagation step 2 and reacts with a Cl2 molecule, producing CH3Cl and reforming that chlorine radical. So again, we're showing it's been reformed, it's not being consumed. And again, add those two equations together and you make the overall equation. You can see straight away, as soon as it's mentioned the word exothermic, I've just a little reminded myself what this diagram needs to look like. So the enthalpy change for the reaction is the difference between the enthalpy of the reactants and the enthalpy of the product. It's a downwards arrow because it's exothermic. The activation energy for the catalyzed route is the pink arrow. So you can see that's the lower of the two curves. And the activation energy for the uncatalyzed route is the higher of the two curves. For the final part of the question, we just need to come up with two ways in which the use of catalysts helps chemical companies make their processes more sustainable. And just remember that for each suggestion that you make, you have to link it to sustainability. So any 4 of these statements was allowed. So the first one there, reactions take place at lower temperatures. So why is that more sustainable? It's because less energy is needed and therefore we're using less fossil fuels, and therefore these fossil fuels can be used for other things, for example feedstock in chemical processes. Less fuels burnt because we don't need such high temperatures. So again, why is that sustainable? Well, we're putting less CO2 into the atmosphere. And then a sort of slightly different angle. Catalysts allow different reactions to take place, and you could then argue that the alternative reactions could have better atom economies, so that's the sustainability part there. You could also say these different reactions may use less harmful substances, and the obvious one I suppose is the one at the bottom there. Catalysts can be reused.